Thermodynamics and Chemistry. The first law of thermodynamics is a restatement of the law of conservation of energy, which states that energy can neither be created nor destroyed in a chemical or physical process. Another way to state the first law of thermodynamics is delta E equals Q plus W, where delta E is a change in internal energy, Q is heat, and W is work. Now, heat and work depend upon the pathway, and so they can be positive or negative. Let's look at a first law problem. We're looking for delta E for a gas, so the system is the gas. And it says the gas absorbs 225 joules of heat, which means Q is positive. And it says the gas does 243 joules of work. So since the system is doing the work, that's negative 243. So the change in internal energy is negative 18 joules for the gas. Internal energy is a state function. It's independent of the pathway. However, Q and W, heat and work, do depend on the pathway, and they are not state functions. If a chemical reaction is carried out in a bomb calorimeter, the system is confined to a constant volume and no work of expansion is done. And since work is 0, delta E in a bomb calorimeter is equal to Q sub V, which is the heat at constant volume. If a reaction is carried out in a container open to the atmosphere, like a beaker, the heat of reaction occurs at constant pressure, and that's called the enthalpy change. Enthalpy, if you remember, is delta H, and that's equal to the heat at constant pressure. Now, assuming the only type of work done is pressure volume work, where work is equal to negative P delta V, we can take the first law of thermodynamics, delta E equals Q plus W, make some substitutions, and get an equation that looks like this. Delta H, which is the heat at constant pressure, is equal to delta E plus P delta V, and that's where the work comes into play, P delta V. So this is the first law. It's just making some appropriate substitutions into the delta E equals Q plus W equation. Consider this chemical reaction. We have a solid plus 12 moles of a gas forming 10 moles of a gas and 4 moles of the liquid. Now, liquids and solids have essentially no effect on the volume because liquids and solids are compressed states of matter. Relatively speaking, they don't take up much volume. Gases, on the other hand, take up a large amount of volume because 1 mole of any gas occupies approximately 22.4 liters. So in this equation, we have 12 moles of O2 being replaced by 10 moles of CO2. We're just looking at the gases. If you go back to the ideal gas law, PV equals nRT. We can get the volume of CO2 and of oxygen from that equation. And from there, we can get the change in volume, which is the volume of products minus the volume of reactants. We're just looking at gases, though. We can substitute into the first law right here and get another equation for the first law that looks like this. Delta H equals delta E plus delta nRT. Basically, there's two ways to find work. I can find work by taking negative P delta V, or I can find work by taking negative delta nRT. Usually, these values are recorded at 298 Kelvin, and so the RT product at 298 Kelvin becomes 2.48 kilojoules per mole. So let's look at this problem here. We want to calculate the work done and delta E for the combustion of naphthalene. Work equals negative P delta V. So that's 1 atmosphere times the change in volume. In this reaction, I'm just looking at the volume of gases. So let me solve for the volume of CO2 first, which would be nRT over P. the ideal gas law. So N, number of moles of CO2, is 10 moles. R is the constant, 0.0821 liter atmosphere per mole Kelvin. Temperature, 298. And pressure is 1 atmosphere. So the volume occupied by this gas, 245 liters. Then I'm going to find the volume of oxygen. Same way, nRT over P. Number of moles is 12.0821. Everything else is the same. Temperature 298 and 1 atmosphere. So the volume of oxygen, 294 liters. I'm ignoring the liquids and solids because they have no effect on volume. So the change in volume is products minus reactants, which is 245 minus 294 liters. So when I solve for work from negative P delta V, I get a value of work of 49 liter atmospheres. We're not accustomed to seeing those units for work. We're used to seeing joules. So I'm going to move to the next slide. And we're going to take that work, which was 49 liter atmospheres, and convert to joules. And there are 101.3 joules in 1 liter atmosphere. So the work in joules, positive 4,960. So that's one way to find work. The other way to find work is negative delta N RT. Delta N is the change in the moles of gas. Well, if you go back to the equation, that would be 10 moles of product minus 12 moles of reactant. R, 8.314 joules per mole Kelvin. Temperature, we're at 298. So when you solve this for work, just an alternate way to solve, we get same number. So either way is okay to solve for work, negative P delta V or negative delta N RT. Both ways will work. We also want to find the change in internal energy for this reaction, which is Q plus W. Q was given to me in the problem, negative 5,156.9 kilojoules. That was the enthalpy change, which is the heat, plus work, change it to kilojoules, 4.96 kilojoules. You'll see that the work is really insignificant compared to the heat. So the change in internal energy comes out to negative 5,151.9 kilojoules.